Welcome all. Till now, we had been discussing the propagation of light in an optical fiber, and we had studied various types of optical fibers and how the signal is propagating through the fiber. We had already seen how the signal get distorted inside the fiber, and from all this knowledge, we had find that we concluded that single mode fiber is the best fiber for long distance communication, offering large bandwidth. Now let us discuss another important topic in optical communication, that is optical sources. Even though light is abundant in nature, there are so many sources of light, but these sources are not suitable for optical communication. The reason is very clear that most of the sources possess large spectral width. Many of them can't be switched on and off at a rapid rate, and therefore it can be used, it can be modulated, and as a result, the sources can be used for sending or carrying information in the optical form. So before getting into discussion of optical sources, we shall first discuss the characteristics looking for an ideal optical sources. The main requirements of an ideal optical source is, is that it should be possessing spatial coherence, temporal coherence, and spectral coherence. So spatial coherence describes the correlation between waves at different points in space. Temporal coherence describes the correlation between waves observed at different moments in time. While spectral coherence describes the correlation that exists between the spectral components at a given frequency in the light oscillations at 2 points in a stationary optical field. So all these three properties are best satisfied in a laser source. So let us see the coherence properties of a laser beam. A light field is called as a coherent when there is a fixed phase relationship between the electric field values at different locations or at different times. That is, it should possess a light field. If a light field to be called as a coherent source, it should possess both spatial coherence as well as temporal coherence. So in this figure, you can see this is a Gaussian beam. As you can see, the beams are equally spaced in space. The brightness is same. So it is possessing a perfect spatial coherence. And as you can see, at different time, the intensity is same. And therefore, we can say it possesses a good temporal coherence. So this Gaussian beam possesses perfect spatial as well as temporal coherence. Let us consider other cases also. In this case, you can see that the spacing between the beams is same throughout, but there is a change in intensity of the beam. That is, at different time, the intensity is varying, and therefore we can say that this Gaussian beam possesses good spatial coherence but bad temporal coherence. In this case, as you can see, The intensity at different time is same, but there is a spatial variance. So we can say that this Gaussian beam possesses bad spatial coherence, but good temporal coherence. Now let's see laser in detail. The basic component of a laser is a resonator. So a resonator is nothing but it's a cavity. We call it as a resonating cavity. Why? You guys know what is a resonator. Resonator means what? It will trap something, say its frequency or wavelength, inside that cavity if and only if some conditions are satisfied. So every resonator will be having a resonant wavelength or resonant frequency. And that resonant frequency is depending on the length of the cavity and refractive index of the cavity. So this particular resonant cavity will trap a particular wavelength only. All other wavelength will be ejected out. So there will be some, this is the ideal case. If some irregularities occurring in the mirrors, as in the ideal case, we are considering the two mirrors as perfect reflecting surface. If any imperfections in the reflecting side, it will result in losses. So as you can see, as I had just said before, the resonating wavelength can be identified is proportional to the length of the cavity and refractive index. So I can from this you can see that lambda is equal to 2NL by Q. Now here to the resonating cavity, I'm giving some gain. As I am giving some external gain, this simple resonant cavity will get transformed to a laser. So resonator plus gain medium is termed as a laser. So laser oscillators versus laser amplifier. So just before we had discussed simple laser oscillator, it will transform to a laser amplifier if to the medium we are giving more and more gain in such a way that we can overcome the losses. Then this will act as a laser amplifier. Laser oscillator plus amplifier, that is master oscillator power amplifier. It combines both the function. Now before going in detail about the laser working principle of laser, it's very important to understand what is spontaneous emission and stimulated emission. In your previous semester, you had already studied the levels, energy band gap and all the things, right? So I'm considering two energy levels, that is lower energy level and upper energy level. As you know, the electrons will always be present in the lower energy level naturally. Once this electron is encountering with an incoming energy which is proportional to the energy band gap, then this electron will absorb that energy and will get excited to its upper energy level. There is simple excitation. So now the electron is in the upper energy level, and for a particular time period that electron will continue to be in the upper energy level. After that particular time period, that is its lifetime, it will come back to its lower energy level by emitting a photon. This process
is termed as spontaneous emission. Now, in the case of stimulated emission, once the electron reaches the upper energy level, naturally it will come back to its lower energy level only after a specific time period, that is its lifetime. So before that, if you are trying to injecting another photon of proportional energy, then this electron will interact with the incoming photon or energy and will get come back to the lower energy level by emitting photons. And this type of emission is termed as stimulated emission. The most important thing of stimulated emission is that the emitted wavelength will be same as that of the wavelength which is inciding on the electron or excited electron.